So let's run this. It ran. And let's look at the matrix. We got a 4x4 matrix that is actually has this block diagonal structure, right? So if we do u equal to a backslash, what do we need to do? Actually 2a backslash e. Wait, I think we get a minus sign here, right? It's because 2a times small a plus b has to be 0, so we have a minus sign here. So let's actually do a equal to minus of this. We get a, which is 0.05 minus 1.
Why isn't it a inverse?
It's this backslash sign. If you wait, yeah, if you do help backslash, you are going to discover that it's actually inverse of a times b. Okay, that's now if you plot x and a, that's our best approximation of the piecewise linear function to the step function at 0.5. All right, and we can see that if we refine this, let's do 30 instead of 3. I mean, the good thing about the program is that you can now change parameters very quickly. And let's actually put what we have typed into here. So this and this. Right. I'm gonna run this. So here's the best approximation of the step function with 30 elements. All right. How about 300? Close this. This is our best approximation of the step function with 300 elements. Right. So basically we can see it gets sharper and sharper, except for, well, in order to get the best approximation, you do have to overshoot a little bit and undershoot a little bit. Yes, it's actually well, I shouldn't say this is similar to Fourier series, but instead Fourier series is actually the best approximation. I mean, if you do Fourier series, if you do Fourier transform to a step function and truncate it and transform back, you can mathematically prove that it is actually a finite element solution to the same problem, except for instead of you are in the piecewise linear continuous space, you are in the Fourier space, which is the space spanned by a finite number of Fourier modes. In other words, instead of using the head functions as basis functions, you would be using what has basis functions?
Sinusoids?
Yes, you would be using sinusoids as basis functions. But if you do go through the same procedure using the sine functions as opposed to these head functions, which would be plotting here is going to be the Fourier series. Okay. So this is in some sense a generalization of what you do using Fourier series. Okay, and this phenomenon, if you did Fourier series, you might know it's called the Gibbs phenomenon, that you have the overshoot and undershoots. Also happens in finite elements. So finite elements in this form also is not a very good idea when you treat functions with just discontinuities. And there are hybrid methods between finite elements and finite volume that deals with this issue. And I believe one of our TAs, Phil, actually works on methods like that, right? Okay. Right. So this is basically the program form of what we discussed in the last lecture. Any questions about this very short program? No. All right.